per unit system. And it's very important for simple reason. If I ask you how many hours you spend in the gym, if you told me 8 hours, it doesn't make any sense. 8 hours a week, a month, a year, it has to be referred to something so I know the percentage. You can say I spend 10 to 20% of my time in the gym. So we call it percent system. If I'm using per unit system, I'm not going to say 20%, I'm going to say 0.2. So that's the per unit system. The same thing we are using in power system and electric machines, used a lot. That's actually in industrial use per unit. Because maybe you have two similar machines, they have the same impedance, but they have different ratings. So how can you compare between the machines? That's number one. Number two, it makes it very simple as you're going to see now. When you use per unit system, it makes it very simple, especially when you are dealing with transformer. Let's first start, how can we calculate the per unit system? Before you start making any calculation based on per unit system, you got to choose the base values that you're going to refer to. Like I said in the example of the gym, I'm spending 8 hours per week. So week is the base that you're going to refer to. The same thing, when you are dealing with the electric circuit power system, electric machines in electric system, so you got first to choose the rating power, the volt amp. So we call it S. So the first choice is going to be S base. And I'm going now talking about single phase. The system is very similar. I'm going to do it in the end, but let's just start with the single phase. So SB means the base and base. Choose the phase voltage rating value. These are the main two quantities you choose as bases. From these two bases, you can derive the rest of the base. Example. Of course, you want to calculate the current in per unit, which is of amp. So you got to find the base or current. So how you find the base of the current? You just divide the SB by VB. So that will be the base for the current. How you find the base for the impedance? The base, call it ZB. You can divide VB by IB, but try to keep any base only refer to S and V. So you want to get rid of I. So we'll say VB. And you know the I base is equal S base divided by VB. So it will be equal to the base voltage square divided by the base power. So that will be the base for the impedance. To take care of the unit. When you find the base impedance, it's the base voltage in volt square and S in volt amp. But sometimes you'll find that the voltage expressed in kilovolt. It's okay, you can do that. Kilovolt base square, but when you divide by mega volt amp. So use mega instead. Otherwise, use only volt divided by volt amp. So that's the impedance. So now we have everything, because you can find the current, the voltage. How you calculate per unit value? For example, how you calculate the current or the voltage? The voltage per unit, you write like that, is equal the actual voltage. That's the actual value divided by the base value. You get it in per unit. How you find the current per unit? I per unit will be equal to the actual value of the current divided by the base value of the current. How you find the impedance in per unit? The actual value of the impedance divided by So in general, if you want to find any quantity in per unit, you just divide the actual value by the base value. So we'll just say the general rule, per unit, quantity per unit will be equal to the actual quantity divided by the base value in general. In transformer, we have some differences that we are going to face. Let's say that's transformer. I have primary, you have secondary. Yes, it has the same volt amp, right? Volt amp, primary, second, the same. Let's just call this one side one, and that's side two, for simplicity. But you got voltage base side one and another value on side two. So that will make difference now. Yes, you have now two quantities for each side. So this side you have S base and VB1. On this side you'll have S base and VB2. From these two quantities, you are going to derive I. You will have different, for example, IB2 will be equal SB divided by VB2. However, on other side, to find the base current for side one will be equal to S base divided by VB1. The same thing for Z. If you want to find the base impedance, will be equal to voltage base 1 square divided by SB. And for this side, so that's 1, that's 2. It's equal to VB2 square divided by SB. So we'll have on each side, whatever is connected to the primary side, I mean side one, if it's connected to another impedance transmission line, the base of this side will be the same for side one. If you have anything connected to side two, the base value used for side two is going to be applied for the rest of the circuit to the right. Okay. Let's take an example for that. And here's transformer. But before we go to transformer, let's assume that we're going to solve problem using equivalent circuit. So usually you are going to have equivalent resistance and equivalent reactance. So that will be the equivalent impedance. The question now that which side this one? Is it side one or side two? It's very interesting, and that's the first advantage of using per unit system. The equivalent impedance, it doesn't matter on side one or side two. Both are equal in per unit. That's one advantage. It doesn't matter which side you're working, one or two, all will be the same. But when you want to find the actual value, you got to multiply by the right base. If you want to find the values of current voltage on secondary side, on side two, multiply by the base of two. If you want to find side one, multiply by base of one. But the equivalent circuit, if you do it doesn't matter. It has only one value. There are no two values. It doesn't have side one, side two. We don't work for both sides. That's much better, right? So that's one advantage. And that will be V1 per unit. And that one will be V2 per unit. We don't have dashes. No I2 dash, no I2. And that will be current. And I'm not going to write 1 or 2 or 2 dash. I'll write current per unit because it will be the same. Another thing, the impedance here has equivalent resistance, R equivalent per unit, and you have X equivalent per unit. Amazing. The value of R equivalent per unit, the R equivalent per unit of the transformer is equal the per unit value of the copper loss in the transformer. per unit. The resistance per unit equivalent is equal to the copper loss. So the copper loss per unit will be equal to equivalent resistance per unit. Amazing. If you want to find the value of the equivalent resistance, find the copper loss multiplied by SV, you'll get the power. It's just simple. Okay, let's just, we're raising, the per unit a lot, so let's just solve an example. Here's a single phase transformer has the following data: 10 kVA, 2220 voltage, 60 hertz. The equivalent impedance, the right side, it was found equal 10.4 plus J 31.3 ohm. And the following: the equivalent circuit diagram. In per unit. Unit. E per unit voltage regulation. Does that write VR voltage regulation, or I have to write split it out? That's fine. Okay. Okay. When mention when you want to find the voltage regulation, when the transformer is 75% of the full load at 0.6 power factor lagging. So how to solve a problem in per unit system? What is the first step? Choose the base. But if it is not mentioned in the problem, what's the base you're supposed to choose? What you choose? Because they should tell you the base of the voltage is equal 1,000 volts, S base is equal 2,000. So what happens if it's not given to you? What do you think you are going to do? How you choose it if you don't have if you don't have any value given? Well, side one or side two, what you're going to choose? Let's say side one. What you will choose? Okay, so in other words, that you are going to choose the rated values, right? Exactly. You get the values. The rating values of the transformer, and that's usually what they do in industry. They use the rated value because you want to refer everything to the rated value or nominal value. So, and since you have the transformer, so you got two sides. So I'd like to just sketch the transformer like that, and I put each value on both sides. This side one, and that's side two, and I will check. Of course, S is the same for both. That's equal to 10 kVA, which is equal to 10,000. And for the side one, you have the voltage base 1 is equal to 2200 voltage, and base 2 is equal to 220 voltage. That's the first thing. That's the first thing you do. And S base is the same for everything. Now I will start to get the current base and Z base for both sides. First, what's the I base? I will divide S base, which is 10,000 volt amp, divided by the voltage V base, which is 2200, and I get 4.55 amp. And I will get the base impedance ZB1 will be equal to the voltage square divided by S. The voltage square on the side will be 2200 square divided by the base 10,000, and I get in ohm the value which is equal 483.52 ohm. All right, I'm done with the side. We'll go for the side 2. I'll do the same thing. I will have I base 2 equal S, which is the same, 10,000 divided by the voltage 220 will be equal to 5.5. And by the way, you don't have to value on the secondary and the primary, they are related by the turns ratio A. For example, what's the ratio here? The turns ratio of the transformer will be 2200 divided by 220. So we get 10. So look at I base 2. What's the ratio between I base 2 and I base 1? It's equal A times IB1, right? So you can do that. If you can do it faster, it's better. So it's equal A times IB1. You could do it like that. 10 times what you got before, 4.55, which is equal 450.5 amp. The same thing. What about the impedance? The same thing. You can do also. You find the ZB2. Let's just use first the formula. BV square, in this case, 220 square divided by 10,000. What you will get? You will get 4.835 ohm. Again, you can use the relationship between the impedance on the secondary and the primary. We know that ZB2 is equal to ZB1 divided by A square. If you divide by 100, you get the same thing. So you have two choices. You always try to choose the fast. That doesn't take time. So I'm ready. Once you have the basis, you are ready to do start solving the problem. So the first thing in this example that we need to find the equivalent circuit. What do they mean by equivalent circuit? The equivalent circuit will be like that. You have resistance, you have reactance, and that's it. Big problems like that. So I need to find R equivalent per unit. And I need to find X equivalent per unit. Observe, I don't use RE1 or RE2, or just RE. Well, so what I have the equivalent impedance on side 1. So to find the per unit, I supposed to use the base of side 1, right? So which ZB I'm going to use? ZB1, right? So I will say Z equivalent, I'm not going to write 1 or 2, per unit equal to, I got 10.4 plus J 31.3 divided by ZB1, we already got it, 483.52. And I divided by each term, 10.4 divided by this number, 31.3 over its number. That's what I get. 0.0125 plus J 0.0647. And what is the unit? Per unit. And then what I'm going to do, replace the values here. That will be 0.01250, and that will be J 0.0647 per unit. I'm sorry, that's not ohm, that's per unit. All right. You have here, I have V1 per unit, I have V2 per unit. That's the equivalent. And the current will be here I. And now we're going to see the advantage of the calculation. Any question? All right. Let's see part B, calculate the power, the copper loss at full load in per unit. So let's do it. I know that we mentioned that it's equal to the equivalent resistance per unit, but just let's do it. Let's assume we don't have R was given the problem. What you will do? I will try to find the copper loss and then divide it by the base, the power base, SB, right? So we'll say part B, need to find the copper loss at full load per unit. So it will be equal to copper loss at full load divided by the base. What is the base of the power? Yes, I know that we give S base. Should you get power phase, reactive power phase? No, S base works for any type of power. So you will divide just by S base. Yes. Trying to find the per unit value. So I divide. Did you pay attention the first one we did? How you find the per unit? That's the impedance per unit. Is equal to the actual value of the impedance divided by the base value. So the base value, this is the base value. Per unit is equal actual value divided by the base value.
Why did you use this?
Because the impedance, the equivalent impedance was given side one. If it was given side two, I'll use ZB2.
Oh.
Thank you. Any more questions? Because after this example, they are going to solve something by yourself. So ask. Advise. Right. Right. Now, we need to find the copper loss, the actual value, and divide it by the base. One base, by the way. We don't have for both sides are the same base. So how you find the copper loss? Copper loss in general will be equal to I square R equivalent. So it depends. Now when you're calculating the actual value, you got to find if this is given. So you have to add I on side one. But you see, that's ugly. Yes.
Is this going to be for?
Yeah, that's right. 483.5. 483.52. Yes. Thank you. That's all. That's all. That's the way you're going to do it. In general, if you have the actual value, you find the peak copper, I1 square, RE1, divide by RE1, and then you divide by the base after that. That's, of course, full load. That would be full load. That's the way always we used to do. Yeah. But how to do it in per unit? How you can do it in per unit? Well, let's calculate it. What is the current full load? How you find the current at full load? Rated power divided by rated voltage. Yeah, volt amp divided by voltage amp. That's right. So, and it said full load. The copper loss at full load. So we are going to use the full load of SB. What is the SB? It's 10,000. amp. What is the rated voltage on side 1? 200 voltage. So you get the full load current, which is equal 4.55 amp. Now we are going to use this value. You multiply by the equivalent resistance and you get copper loss. Let's do it. So it's equal to 4.55 square times the equivalent resistance, which is equal to, it was given the problem, 10.4 ohm. So I multiply it by 10.4 ohm. You get the copper loss, actual value on watt. You got it almost equal to 15 watt. So that's the actual copper loss. Okay, you are almost done. Yes. You cannot multiply actual value of per unit. You multiply per unit. I'm going to do the second method when I'm using only per unit. Okay. But this one is I'm using just everything in actual. So we found the. You have a question? The same thing. Okay. So to find the copper loss per unit, I divide the actual value, which is 215 watt, by the base power, which is equal to what? S base is equal to 10,000, right? Yes, 10 kVA. That's S. 10 kVA. What you get? You get 0.0215 at full load is equal to what? 0.015, which is equal to what? The transformer period is equal the full load copper loss in per unit. So we prove it. Yes. To find the copper loss per unit, I divided the copper loss, the actual value in watt, when I got I square R, and I divided by the base power of the base power SB. So the base power was given, that's the base, the rated value, base value of volt amp, because it's power. So when I divide power by power, I get per unit. So how I calculate the one per watt, I got I squared times R. And I got the value in watt. This is right. That's 215 watt. Then I want to find it per unit. So I got to refer to the base. What base are you going to use? Volt, amp, or power? Power, because you divide power by power. So what is the power of the transformer base that we use? It's 10,000 VA. So I divide by 10,000, I got 0.0215. And when I observe that, compare it to the resistance, I found it's equal to equivalent resistance per unit. It's the same. Yeah. And per unit, the same.
Yeah, but you got it wrong.
I got what?
On the equivalent unit. Yeah, 0.25.
That's right, yeah. Yes, I wrote a flip. Oh, okay. That's point. This even written wrong, yeah? That's point 0.0215. Yes, flipped, yes. 0.215 per unit. Yes, yeah. So the same. I can calculate per unit. And let me, if you want to calculate the copper per unit, I know it's equal I square times R equivalent, right? When you use per unit, you don't write 1 or 2. I per unit multiplied by R equivalent per unit, right? What's I per unit? The current per unit. I'm saying full load, right? It means full load, it's equal to the base, be equal 1 per unit, right? And the base is full load, so what you get? 1 per unit. Let me just write. What's the current per unit? It doesn't matter any side. But let's say a side 1. So you will have the current actual divided by current base. I'm using I base, the full load, and I'm using. So you can say the full load current is equal 4.55 amp, and the base current on this side 4.55 amp. So I get 1 per unit. And that's the beautiful thing. When you have the volt should be 1 per unit, the current be 1 per unit, because you are using the same base. So what is the R equivalent per unit? We just got it. It's equal 0.0215 per unit. So when you multiply, when you get the copper loss per unit, how you get it? You will see it's equal to I square per unit, which is 1 square, times R equivalent per unit, which is 0.0215. You get 0.0215 per unit. That's why the R equivalent in per unit equal to at full load per unit. So you don't have to calculate every time. Now it's obvious. All right. Any question on this one? Yes. For 0.55. That's what that's here. I got the full current, the full load current. I divided S by voltage, the rated value of the power, and by the rated value of the voltage. Part C, they ask for the voltage regulation. Part C, they need to find the voltage regulation in per unit. And they give condition, they said that the current was 75% of the full load. At 75% of the full load, and power factor 0.6 power, 0.6 lagging. Okay. It means using, when you said that, it means they're using the rated value on the second. All right. I'm going to use per unit. How you are going to use per unit? First, if you are not using per unit, how you find voltage regulation? I gave you before in the transformer 2 formula. One, if you are referring everything to the primary, and another formula given when it's referred to the secondary. If it's referred to the primary, you have V1, right? And the other one, V2, will go be V2 dash. And divided by V2 dash and times 100. That's the voltage regulation on that. And if you are doing the other side, you will have V2 minus V1 dash over V1. So it's just simple. What about per unit? Equal to, well, V1 per unit minus V2 per unit divided by V2 per unit. You don't have dashes. And this formula work, whatever you are working, what side you are working at. Work in side 1, side 2, this is one. You don't have two formula like the other one. So you need to find the V1 per unit, the V1 per unit and V2 per unit. Okay. Well, I'll go back to the transformer. The equivalent, this one. Oh, it's messy. Well, that's the transformer resistance 0.215 and 0.0647 per unit. And I'm going to use load now. And that will be V1. Just to make this V2 dash. No, I write per unit and V2 per unit. But he said at rated value of the voltage, it means that's equal to what? Once they say working at the same value of the base you choose, it's 1 per unit. Because you divide the value by itself. What about the current? Current, they said 75%. 75% of full load. What's the full load per unit? Primary or second? The full load current in per unit on the primary side. And the base is full load, I'm dividing the value by itself, right? One side, right? What about the second side? you are using different base, then you got to calculate the actual value of the current and divide it by the base, the new base. But if the base current is the same rating and the current you are using the same rating, so it's one by one. But in this problem, they said that the current, or they are delivering 75% of the rating value. Let me just write here. If the current equal I full load. So what is the current per unit? You will say I full load divided by I base. But in our case, I base is equal also full load. So in this case, we have 1 per unit. What about if I say the current is 75% of the full load? So what is the I per unit in this case? 0.5 I full load divided by I full load, which is equal to what? 0.5, yeah, 0.75 per unit. So the current here, 0.75 per unit. I1 or I2, it doesn't matter. Both are the same. So that's the current. So look at the circuit now, it's very simple. You have voltage equal 1 per unit and angle 0. Take as a reference, the vector, and the current is equal 0.75 per unit, but we still have to find the angle. The angle, the power factor. They said the power factor 0.6, lagging. So I got to fix this one, not only magnitude and also an angle. So how you find the angle? That's, you know how you do that. If so, phi will be equal negative sign because it's lagging. Cosine minus 1.6 will get negative 53.13 degree. So that's the angle of the current. So now we can say that the current in per unit is equal to 0.75 angle negative 53.13. That's the current. Point 0.75 an angle negative 53 per unit. I want to find V1, to find the voltage regulation, right? All right. So how you find the V1 circuit? Just use any circuit here. So the V1 is equal this voltage V2 plus the drop. So V1 all impedance per unit plus I per unit time Z equivalent per unit. No 1, no 2, nothing. V2 1 per unit is 1 angle 0. The current is equal 0.75 and the angle negative 53.13 degree multiplied by Z equivalent, which is equal 0.0215 plus J 0.0647. And you solve this equation, you'll find V1 per unit, you find is equal 1.0486 on angle 9 degree per unit. So that's V1 per unit. Now we have all information to find voltage regulation. So voltage regulation equal to V1 magnitude per unit minus V2 magnitude per unit divided by V2 magnitude per unit. V1 magnitude is equal 1.0486 minus 1 divided by 1. That will be equal to 0.0486 per unit. And you want to get percentage, just multiply by 100. Save a lot of work than the other. So 0.86%, and you got the answer.